Welcome back to another HVAC-Engineering-Techie channel training video. Today's video is on basic electrical for building systems. This module basically goes over the basics of electricity. As a background you will need to be able to be a commissioner or a technician or electrician. So basically it's real basic stuff, but we'll go through this. It's not a real long video, but it does kind of get you up to speed on what electrical systems are. Remember, HVAC-Techie is the thing that talks all things about HVAC and building systems, including electrical. So appreciate you being a subscribing member. If you're not, I'd really appreciate it if you become one. All you have to do is press that subscribe button down below. Give me a thumbs up if you like the video. Costs you nothing. It's absolutely free and no one will ever bug you. It just helps me because Google uses that to evaluate the video. So I appreciate it. Thanks. All right, let's get started on building electrical systems. All right, so now we're just going to take a look at the different videos we have available in our electrical sections. So the first D10 is electrical system design for non-electrical engineers. An electrical engineer will already know all this stuff. It's just some basic power and basic design concepts. S-12 is electric motors and drive systems. S-50 is basic electrical for building systems, this video. And S-51 is electrical power distribution. S-52 is critical electrical power. S-53 is electrical lighting system. S-54 is electrical safety for commissioning. CX-9 is technical commissioning electrical systems part 1, and CX-10 is part 2. I'll break them up because the video was way too long. So basic electrical concept. This is real basic stuff. Just kind of gets you familiar with what electricity actually is. Okay, the definitions. This is a little boring, but they are here. If you need them, you can clip them out of here. A voltage is a unit of electrical potential and electromotive force. Amps is a unit of electric current flow. Ohm is a unit of electrical resistance. Watt is a standard unit of measure for electrical power. EMF is electromotive force. kW is a kilowatt, 1,000 watts, real power. Kilowatt H is kilowatt hours. And kVA is a kilovolt amps, which is apparent power. kVAR is kilovolt amps reactive. It's power stored in motor magnetic fields. RMS is the root mean square, average of the squares for each instantaneous value of current. We're going to talk about that. Inductance, an electromotive force that is induced by the process of electromagnetic induction between two circuits. Capacitance, the property of a circuit element that permits it to store a charge. Reactance is the opposition to the flow of alternating current caused by the induction and capacitance in a circuit rather than by its resistance. Impedance, a measure of total opposition to current flow in an alternating current circuit, made up of two components, ohmic resistance and ohmic reactance. It's getting a little bit of my pay grade, but that's what the definition is. Phasor diagram, graphic representation of the angle of the phase of the neutral voltage and current. Harmonics, a repeated ripple in the power waveform at a definable frequency or harmonic of that frequency. And we'll explain that when we get there. System resonance, large spike of current and voltage caused by harmonics and harmonic or harmonic corrective and power factor corrective devices. So this can actually change the current and voltage in a system if you have resonance. Commutation is a quick voltage drop in a waveform caused by a phase overlap in an inverter. Again, electronic stuff causing problems, but these you don't want. Either this or this you really don't want in our distribution systems. Now in electronic circuits, they design them to take advantage of what these do, but in our systems, we'd rather not have them. Ohm's law is E equals I times R, which is volts times amps times ohms. In electrical world, E stands for volts, I stands for amps, and R is for resistance, for ohms. Basically, that's pressure equals current times resistance. If you're a mechanical guy, you can maybe understand that better that way. I equals E divided by R, which is amps equals volts divided by ohms. Current, pressure, resistance. R equals E divided by I, which is a formula just done in another direction. Electrical power is the P equals I times E, and the P stands for watts, amps times volts, power times current times pressure. P equals E squared divided by 2 times R. That's watts equals volts squared divided 2 times the ohms, if you want to use ohms. Much easier to use this one. Work power times time. So kilowatt H is 3,413 BTU. If you need to convert between kW and BTU. 1 kW was 1.341 horsepower. Alternating current, we're going to talk about that. What is electromotive force? So the instantaneous volts is represented by the sine of this angle times E. And that is the basically equation for instantaneous volts. This is kind of how it's lying. If you have a generator here, and the generator is turning this direction, and it starts at the top, and as it starts here, zero angle, starts here, and it rotates this way until it starts here, gets to 90 degrees right there. Put it right there. Then it goes from there to there. That's 90 degrees going down to 180 degrees. It gets to there, it goes to there, and then it goes on and back to zero when it gets back up to here. So that's the name of the process. It looks like this on our diagrams. So this is zero. This is where it starts right here. This is when it gets to here. This is back to zero again at 180 degrees. And this is the sine wave. Now, a harmonic is actually a ripple in this sine wave. Something's affecting that sine wave and the power as harmonic, and it's fluctuating the power, which causes issues with certain solid-state devices in the system and a heating of wire and that sort of thing. So this is the angle of rotation. This is the volts. Because remember that EMF is the force of the voltage. Alternating current in a resistive circuit, average value of a power sine wave is E equals 0.637 times E maximum, and the amps is 0.637. That's the average. So if you got a sine wave, the average is going to be, this is current, this is voltage, this is a resistive circuit. You see they're right following each other, because that's what a resistive circuit is, and the average voltage is going to be right there at 0.637 of the maximum. So you measure from here to here and multiply times 0.637, you'll get the average of that voltage, and it's true of voltage and amps. Alternating in a power sine wave is the effective power. The effective power in a sine wave is a root mean square of the current. It's represented by RMS. And this average of the squares of each instantaneous value of current. And so I equals 0.707 is the average of that. 2 RMS voltmeters read effective power, not average power. So this is the effective power, and they're going to read that. So that's why, if you're a commissioning guy or a test and balance guy, we request that you have true RMS meters. Because if you have an inductive circuit, your meter will not read the amps correctly, because it's reading average amps, and you need to read actual effective amps. To do that, you need a true RMS meter. Alternating current, resistance, reactance. Now this is the circuit we've seen before was a resistive circuit. This is a reactance circuit. And so basically, if the angle is positive, current lags voltage, then it's an inductive circuit. If the current leads voltage, then it's a capacitance circuit. Most buildings are all inductive circuits, and the reason is because a resistive circuit is zero. It doesn't do anything, but if you put a motor on it, it's going to add reactance to it, and then that immediately turns into a power factor, so it's now an inductive circuit. So here's this curve, and this is the voltage, and this is the average power, instantaneous average power with effective power is at 0.7. Okay, alternating current, resistance, reactance, impedance, angle, power factor, single phase out, power factor, single phase AC, kW equals kVA times power factor. That's in a reactance circuit, which is an inductive circuit. Single kVA equals E times I divided by 1,000. Single phase AC kW is kVA in the resistance circuit. kVA equals kW. Three-phase AC power, that's single phase. kW equals kVA times I times the square root of 3 times the power factor. That's a reactance circuit. kW, kV times I times the square root of 3 is a resistive circuit. So there's no power factor in that one. And this is that angle again for an inductive circuit. kVA equals kV times 1 times the power of 3, square root of 3. So three-phase kVA equals E times I times 1.73 divided by 1,000. kW equals real power. kVA is apparent power. Alternating current three-phase. Okay, this is a rotor diagram. This is basically saying we start here at A, phase A, and the system rotates as the generator is turning to phase B and then to phase C and back. It rotates in this direction. And this is for a Y connected load. The diagram looks different for a delta load, but so here's what it's saying is if the impedance angle is positive, then a power factor angle, if it's positive, it's an inductive circuit. If it's negative, then it's a capacitive circuit. So in this one, you can see it starts at A, and it's going this way, turning this way. So you can see that amps is following the voltage, so it's a inductive circuit. And a rotor diagram, if you have a rotor meter, it'll show you that immediately. So this is an inductive circuit shown. Now, the reason this is all important is because you size inductive circuits different than you size resistive circuits. So it's best to have motor loads and resistive loads separated so you don't mix them up. But if not, you have to use the motor load calculation for everything. Alternating current three-phase. Remember that the phases start one phase. That's one whole circuit. Two-phase, that's one circuit. Third phase, that's one circuit. So these represent the three phases they go through. And this is the time, and you'll see that this phase right here, it goes through at 0.01667 seconds is how long one phase lasts. So you can see the phases are fairly quickly. Now, I've had people ask, why does Europe and the rest of the world use 50 hertz and we use 60 hertz? This is a 60 hertz circuit that's 0.167. Well, the reason that happened originally, the way I understand it, is 60 cycles allows you to transmit more power over smaller wires than 50 cycles. And in America, that mattered because we had long distances for transmission lines. So we started with 60 hertz to be able to put more power in less wire over longer distances. 50 cycles give you less. Now, also, I've noticed a difference is in a fluorescent tube, I can see 50 cycles. I can see it cycle. In 60, I very seldom could catch 60 cycles. But 50 cycles, I can see the lights flickering. It's not much, but you can see it a little bit. And so I think 60 cycles is a better application. Of course, that's what I was born and raised with, so maybe that's why. But in any case, there is a difference. Europe didn't require long-distance transmission lines. They do nowadays, but back then they didn't because their generators were close to their usage. And so there was no reason to go to 60 cycles. At least that's the way I understand it. If you know a different explanation, put it in the comments and let me know. I can learn something. Harmonics. There are ripples in the power wave from the increase. This is the power loss in electrical transformers and motors. So the harmonics actually affects the efficiency of electrical transformers and motors caused by VFDs, LEDs, UPS, and electronic equipment power supplies, computers, in other words. Electronic devices pull power in pulses, not continuously. Remember, electronics are not analog at all. They're all digital, so they need to simulate a sine wave. They can't make it automatically. So a laptop pulls power in 2 pulses per cycle. So in that 0.016 seconds, they have pulled 2 pulses. In a VFD or 6 or 12 pulses, they'll do that 6 times in that second time, that 0.6 seconds, 0.1016 seconds, I'm sorry. H. So the way that you figure this out, the harmonic is equal to 1 through 4 times the number of pulses plus or minus 1. And I'll show you an example to make that clearer. So if you have a 6-pulse drive, you take the number of pulses of 6, multiply it first by 1, 6. So then you add 1 and subtract 1. So if you had 6 here, you'd be 5th harmonic and 7th harmonic. And then you take a pulse and you multiply it times 2, the next number here. And that would be 12. So it'd be minus 1 plus 1 would be 11 and 13. The next one is you multiply times 3, the third number here, and you get 18. So it'd be minus 1, 17, plus 1 is 19. And the last one, 4, is 24, and that would be 23 and 25th harmonics. So a 6-speed pulse drive could produce harmonics at all these frequencies. possibility. Frequency of a harmonic is harmonic times 60 cycles. So a fifth harmonic here would be 300 frequency, or a 25th frequency would be a 25 times 60, which is a much bigger number. So you can tell where you've got problems. If you find and you isolate a frequency that the harmonic is the harmonic frequency, then you know which one of these is giving you fits, and you have to figure that out. And the only way to fix these is through isolators. And you can do that. You can isolate that frequency out of the harmonic. Alternating current three-phase. This is a Y transformer we were talking about. See where it has A, here it is, A, going this way, A, B, and C. This is a Y transformer, and the neutral's at the center tap. This is a delta transformer. You can see it's got A, B, and C, going this way, A, B, and C, but it has no neutral. The neutral is, if it has a neutral, it'll be connected in the middle of one of these Z windings, and that's a delta load, and we'll talk about that in a minute. Standard American voltages. Europe is kind of the same, but they don't have 110, they have 220. Single phase low voltage is 120 to 240, 3-wire. Three phase low voltage is 208 to 120, 4-wire. 480 volt, 277, 4-wire. 40 volt, 4-wire. And 600 volt, 4-wire. You can go higher voltages, which we'll talk about, but those are the normally distribution voltages. Standard American voltage, built-in median voltages, three-phase median voltage is 4160, 2400, 480 volt, 7200, 4160. Building site higher voltages are normally three-phase 12,000 volt, 12,470 / 7200, 13,200 volt, 15,000 volt. Standard distribution voltages for main distribution 115,000, 138,000, 161,000, 230,000, 345,000. This is the most common, by the way. 500,000 and 765. They can go this high. Nowadays, they're even transmitting million volts. The problem with these real high voltages is they do provide some issues with power loss. And actually the arc distance gets pretty heavy on these. I think this one here is about 14 feet, if I remember right. Sub-distribution panels are lower, 34.5, 46,000, 69,000, 115,000, this being the most common, 138,000. This is what runs around in your neighborhoods. This one is out of the main distribution lines, cross country. Local site distribution is 12,470 as a site, 13.2, 15,000. So you can distribute around local sites that way. Now, you can't have a building running 12,470 in a building. That's the highest I've ever seen inside of a building. But you can have that if you have large generators, say, that are 12,000 volts. You can have that higher voltage. Standard voltage tolerances, 120 volt. So 120 volt is range is tolerance is 126 to 108 volt. And the reason it's 108 volt is because the problem with 108 volt is a minimum incandescent and fluorescent bulb is 110 volts. If you get below 110 volts, they may not fire, whereas an LED they will, but these others may not. So we've always said 110 is a minimum voltage in our systems. 208, 213 is 208 is 218 to 191. 240 is 252 to 220. 277 is 291 to 254. 480 is 504 to 440. So those are basically the tolerance ranges in our systems. Transformers, this happens to be a single phase 480 volt transformer. That could be anything, single phase. And there's ideal transformer formulas, and you need that. You can do that. This is the amps, and these are the volts times the different levels. I've never had to use any of these equations, but if you need them, you got them. Standard transformer efficiency is from 85 to 95%, which means an 85% transformer will run a lot hotter than a 95% transformer. Now, that's a pretty significant difference. So if you have a job that you're trying to find energy on, you got a bunch of 85% transformers, think about moving those to 95% transformers. All right, so this is a 480 volt single phase to 240 volt two phase. You can see this is a transformer of the winding, the 40 volts coming in here, single phase. And then we have these windings. So we have a neutral to ground. We have a line 1 and a line 2, and these are both 120 volts, 240 volts across the phase. This is a 4160 volt three phase to 40 volt three phase Y. So this is a delta coming in. So this is the 4160, this happens to be 4163 phase, coming into a delta configuration, and the output windings are a Y configuration, and they are 480 volt, 277, 277 everywhere. So that's a normal transformer. We see this one a lot. It may not be 4160, maybe some other voltage coming in, but that could be the case. Or this is a delta Y, and this is a 480 volt to 208 volt three phase. It's 40 volt coming in, and then the output of the transformer is in a Y configuration. And you can see the neutral is at the center tap. And so we have 208 volt across all three legs, and we have a 120 between any leg and the neutral. So this is the standard workhorse transformer of our buildings for plug load and small HVAC load and lighting load. And then we have a special transformer, which we can use a delta-delta, which comes in at 40 volt delta and goes out at 240 volt three phase, 240 volt. Now the problem with this transformer is because this delta has no neutral connection, they make it up by putting in a center tap, which means from this neutral to leg C or A is fine, you get 120 volt. But if you do it between neutral and B, which is not connected to the center tap, then it's a high leg, and it's usually 190 to 208 volts. So it's not 120 volts. You have to be careful that you never use what we call the wild leg on a delta-delta transformer. And I figured out right away if you measured voltages and you notice this leg to neutral is not correct. So you only want to use these two power legs for 120 volt load. Power path. All right, so now remember that the power plant's making power in three phase, and it's shifting it out, and every other cycle it's negative back, right? So it's shifting in and out. That's the way electricity works, right? But the grounds are using the earth for the ground source, which is somewhat of a problem. And it means that basically the earth circuit is far lower impedance than this circuit here. So if there's ever a problem and the energy can't get back here, it will come back here. And that's a problem because that puts electrocution at a risk. So remember, never place yourself between a high current load and an earth source because it has high impedance and it will definitely be the favorite conductor. The favorite conductor will be to you, to the earth, back to the power plant, when it really should be in the wires. So you need to be careful with that. Okay, electrical systems for buildings. We have electrical power distribution systems, electrical ground systems, critical electrical power distribution systems, which are for systems that can't afford to have down power, so they have more than one power source, critical system, electrical lighting systems, security alarm systems, fire alarm systems, data and communication systems, audio and video systems, lightning protection systems, protect the building from being hit by lightning. They don't actually stop them from being hit by lightning, but they take that lighting and get it to ground so it doesn't damage the building. So electrical power distribution systems, you're going to see that they have the power of all the different switchgear and panels. And the next video, we'll talk about this in detail. So this is normal building distribution voltages are 480 volt three phase, 240 volt three phase, 208 three phase, 120 volt single phase. And higher equipment voltages, you can do 4160, 2400, or 12040, 7200. So those are also voltage you can use for the system. Electrical ground systems. So the ground systems are important to keep things safe. So basically we normally have a continuous ground system between all major components and panels and transformers. So normally they have that way, but especially transformers. And this continuous bond cannot be a bolted connection. It needs to be a welded connection or a crimp bond. It can't be bolted. So that's the only thing you kind of watch for is on major ground systems that it is a continuous ground. So this is critical electrical power distribution systems, which are like for data centers, telephone centers, hospitals, things like that that can't have a power be down. And this has to be a tier 4. There's a National Uptime Institute that describes tiers. You go all the way from tier 1 to tier 4. And that describes how important the backup power is. So this happens to be a full labeled system, and you'll see what happens here is we have feeder A. This is coming from one substation for the utility, comes into a bunch of switchgear and backup generators. UPSs, the whole thing, PDUs to the critical systems, and then it has power feed B, which is coming from different power stations. It has backup generators on that, different UPSs, central motor control center. So everything is backed up from a different power source. This is tier 4, and this is the facility types, might be data centers, healthcare facilities, critical manufacturing, and telecommunication infrastructure. This is really expensive stuff, but this is the way they're rated, and this is what all the different backup systems mean for critical power. Electrical lighting systems, exterior yard parking lighting, so we have lighting for areas, have high bay lights and interior building lighting. We have lighting control systems that control these different lights. Those are different kind of lighting systems within a building. Security alarm systems, card access, CCTV, which is camera systems, intrusion alarm, burglar alarms, asset protection systems, which is like protect real critical equipment. Fire alarm systems, basically are for protected premise fire alarm systems, supervisor station fire alarm systems, smoke control systems, manual fire reporting, FM gas and CO2 fire control systems, fire sprinkler alarm and control systems. Data communication systems is our data backbone for computers in a building. Local area networks, wide area networks, telephony systems, which are telephones, IP telephones, private cell phone networks, internet access IP, video conferencing backbone. So that's communication systems. Audio-visual systems or TV and radio distribution systems. These are becoming much more prominent now than they used to. Video recording and distribution systems, background music and white sound generators, intercom and public address systems, nurses' call systems in buildings. There are other systems, but these are basically the audio-visual systems we put in most buildings, and clock systems. Clock systems used to be a pretty big thing because they had to run wire to them. Now they're all wireless, so they keep track. And that's intended for like school systems or hospitals, and all the clocks say the same time. So you don't have to go around and adjust clocks. They're automatically on the right time. Lightning protection systems are systems that protect a building from lightning. And normally we have spikes, grounded spikes that are on the high points of the buildings, and that anything that's metal on the roof is all grounded to this system. And this is fairly large cable that runs around that will take the voltage and current from lightning strike and put it into earth ground. This is what a typical spike looks like on a parapet wall. And this is kind of like how it looks like goes around the building. And this is the different ground systems. You can see these are multiple ground rods or ground mats that might be out in this place to take care of it. And these are all isolating power to ground. And that's basic electricity. So that was pretty painless, I think. But just kind of give you a little feel for what really electricity is and some key pointers and what systems we use in what systems are in electrical systems. So now the other videos will take you into detail of all those systems. All right, thank you for watching. I really appreciate it. If you got any questions, put them in the comments below. I will answer them eventually. And thanks for watching. I really do appreciate that. And have a great day, and I'll catch you on the next one.